Nissan's R34 GTR is undoubtedly one of the most popular and recognisable cars to come out of the Japanese street car scene. It's a car that turns out to be infinitely tunable as well, particularly with the very popular RB26 and a market of parts available for getting just about any amount of power you could hope for out of that particular engine. Given the current cost of these cars as well as the relatively low volume they are produced in, though, finding one to actually work on is not that common. We've been fortunate enough that this R34 behind me has come in for some light modifications from the owner that works across the street. Now, as the car was delivered, it's had some light modifications made to it. In particular, it's got a set of apexi low mount direct replacement turbochargers. It's got an exhaust and intercooler upgrade. It's running a slightly larger fuel system with a bigger in-tank pump, a sard fuel rail, 800cc sard injectors, and a sard adjustable fuel pressure regulator. The whole combination was previously tuned and controlled by an apexi power FC, so it's a pretty popular combination for these cars when we see them imported out of Japan. The apexi power FC in particular, probably one of the more popular ECUs over in Japan. In order for that power FC to work, the car's also been fitted with a set of larger Z32 airflow meters. Again, a pretty standard upgrade for lightly modified GTRs. The problem with the stock twin airflow meters is that they basically can be pretty easily maxed out, and when we get to that point we can increase the boost pressure further, but the output from the airflow meters is already maxed out, so the ECU doesn't actually see any additional airflow, and we get to a situation where as we increase the boost pressure, the engine starts to run lean. The owner brought this in because he wanted, first of all, a bit of a health check on the current state of tune, as well as to take advantage of some of the upgrades available on the more modern crop of ECUs. In particular, we chose an Emtron KV8 to go into this car. Now, first of all, before we made any modifications, we put the car onto our mainline four-wheel drive Pro Hub dyno and laid down some baseline power pulls. The car's fitted with a Blitz electronic boost controller, so we ran the controller through its 4 boost presets. On the highest boost pressure, the boost peaked at about 23 psi and then dropped off to about 22 psi at higher RPM. At this boost level, the car laid down a pretty impressive 485 horsepower at the wheels. There was a small problem though. At higher RPM, we were starting to get some light intermittent knock present. This is a #1 killer of performance engines, so it's something that we absolutely need to stay away from, and something that we were intending to address with the new Emtron ECU once we got it up and running. The reason why we may end up encountering detonation is a number of possibilities. Generally, this all comes down to the heat in the combustion chamber becoming so great that pockets of unburned fuel and air spontaneously combust. So things that can cause this would be a low grade or low octane fuel. In this case, we're running on our local 100+ octane pump fuel, so it's about as good as we can get here locally in Queenstown, although yes, there's definitely better fuels available. The other things that can cause this are excessive boost pressure, and in this case 23 psi peak dropping to 22 psi. It's definitely manageable on that fuel. Another aspect could be our air-fuel ratio. As we lean out the air-fuel ratio, this creates more heat in the combustion chamber, which can promote detonation. And the other aspect, of course, is if we run too much ignition timing, this can also cause detonation. So with our base runs out of the way, it was time to get to work and actually fit some components to the vehicle. We weren't making any massive changes here. Given that the Emtron KV8 ECU no longer requires the Z32 mass airflow sensors, the owner had provided a G-Ready intake kit that allows us to remove those mass airflow sensors. And this should also provide a slight improvement improvement in airflow into the two apexi turbochargers. Another modification we chose to make to the engine configuration was to the trigger system, and the factory Nissan 360-degree optical trigger system is well known for giving problems, particularly with aftermarket ECUs. That 360-degree optical trigger literally has 360 little slots around the outside of a trigger disc that are picked up by an optical sensor. This means that the ECU is receiving 180 little reference inputs or engine speed inputs for every crankshaft rotation, which is quite a lot of information and certainly more than the ECU needs. And the problem here actually isn't so much the resolution or frequency of the engine speed inputs, but it's the location of that sensor, which is fitted to the front of the exhaust cam. Now, harmonics in the valve train can play havoc with this and causes cam belt whip, which then affects the signal that is going through to the ECU. This tends to be made worse when the engine is fitted with aftermarket cams. I haven't actually mentioned that yet, but the engine is fitted with a set of tomei cams and aftermarket cam gears. To avoid this, the preferred technique is usually to go to a full crank trigger system, where the engine speed information is referenced directly off the front of the crankshaft, and the factory position on the front of the exhaust cam is used for an engine synchronization input to tell the ECU whereabouts in the engine cycle it is. Now that works great. It's been well proven in several RB26s producing 2,000 plus horsepower and revving to 10,000 plus RPM, but this is only a mildly modified engine. We're not exceeding the factory rev limit of 8,000 RPM, and a crank trigger system is expensive. In this case, the owner opted to go with an NZ wiring trigger system, which fits in the stock location. This gets rid of the 360-degree optical trigger, and instead it replaces it with a CNC machined 24-1 trigger wheel that's picked up from with a reluctor sensor. This means we actually only need one sensor instead of two as well. The reason we can get away with this is that the missing tooth gives the ECU all of the information it needs, given that it's on the cam. The camshaft spins at half engine speed, and because there are two full engine revolutions in one engine cycle, it's seeing that missing tooth once per engine cycle, which is exactly what the ECU needs in order to know whereabouts in the engine cycle it is. Now, this particular system has proven to be a reliable upgrade in lightly modified RB26s, and while no, if you're building a 2,000 plus horsepower, 10,000 RPM monster, this is not going to be the choice. It's a massive cost saving over a full crank trigger system. Worth noting here that this type of trigger system is only compatible with certain ECUs. They will need a trigger mode to suit, so there is no way we could have run this with the existing apexi Power FC. The other sensor we chose to fit while we were installing the Emtron KV8 was a Bosch LSU 4.9 Lambda sensor. This is fitted to the exhaust system and it's wired directly to the KV8 ECU, and this allows us to see air fuel ratio data in real time on the tuning software on our laptop. It speeds up the tuning process because we can use an auto-tune functionality to automatically or quickly tune the volumetric efficiency table numbers. And once we're finished with our tune, we can also place the ECU into closed loop fuel control mode, meaning that the ECU is allowed to make small adjustments to get our air fuel ratio onto our target if there are small fluctuations day to day. The KV8 ECU itself was a cinch to install because it comes here with a plug and play harness adapter straight from Emtron. So it's literally a case of plugging that into the Emtron ECU at one end and connecting it to the existing Nissan header plug at the other end. We did, however, need to add a 4-bar map sensor because in stock form the RB26 doesn't actually use one. Just to be clear, yes, there is a map sensor fitted to the engine bay, but in this case this is solely for the Nissan multifunction display in the center of the dash, and it doesn't actually function to the ECU at all. Once we got the engine back up and running, it was time to put it through its paces on the dyno and get the tune dialed in, which turned out to be relatively quick and easy to do. In this case, we do need to use a special 4D mapping to take account of the individual throttle bodies, plus the fact that we are running a turbo boosted engine. In this case, the main volumetric efficiency table is referenced on throttle position. We then have a target air-fuel ratio table that uses manifold pressure as the load axis, and then we'll find that at high RPM and high boost, when the turbos start to become a bit of a choke point and fall out of their efficiency, we're going to find that the volumetric efficiency of the engine will drop off, and we can compensate that with a four-dimensional secondary load table. Now, it might sound a little bit complicated, but the reality is once we understand how this system works, it's really easy to get up and running and dial in. Now, as I already mentioned, previously it was running 485 wheel horsepower, and we were seeing some inconsistent light knock at high RPM, particularly when the air temperatures were higher. So on face value, I was expecting that we would probably end up actually pulling the power back a little bit. Now, it's important to understand this as well. A lot of people bring their cars to the dyno really chasing a number for internet bragging rights. The reality is that what we ultimately want is a safe and reliable tune. It doesn't matter how much power your engine makes if you're going to be rebuilding it once you get about 2 kilometers down the road. We don't want that. We want a reliable tune. So if we're going to sacrifice 10 or 15 horsepower and we're going to stay away from knock, then personally that's the style of tune that I'll take every time. In this case though, once we got up into the higher boost levels, I actually found that the engine was taking a reasonable amount of timing, and it was relatively immune to knock. And pleasantly, we also found that we were well up in power. On the best run, our dyno registered 528 wheel horsepower on that same boost setting, 23 psi, dropping away to 22 psi, despite the fact that we're obviously significantly up in power. During that run, there was not a hint of any knock occurring. So why was this the case? Well, this is a really good lesson to take away from in this particular case. Always trying to experiment and see what your particular engine wants and needs. On the existing tune, under wide open throttle, 22 to 23 psi, we were seeing air-fuel ratios around about 0.82 lambda. If you prefer to work in air-fuel ratio units, that's around about 12.0 to 1, 12.1 to 1 air-fuel ratio, which is admittedly reasonably lean, particularly for that sort of boost pressure. On the other hand, I chose to go with a slightly more conservative air-fuel ratio target around about 0.78 lambda, and again in air-fuel ratio units that's around about 11.5 to 1. So this is the key difference really between the two tunes. Now, the advantage of going to the richer air-fuel ratio is that we're injecting more fuel into the intake. That additional fuel is going to help because it has a cooling effect on the combustion charge temperature. Remember I said that the temperature in the combustion chamber is one of the key drivers that causes detonation. So anything that we can do to reduce the combustion charge temperature will help make the engine less susceptible to knock. So by richening the air-fuel ratio from 12.0 to 1 to 11.5 to 1, that's actually cooled the combustion charge temperature enough that I can run a little bit more timing, and as a result, the additional timing plus the richer mixture has shown a significant improvement in power, but most importantly, given us more reliability. Now, this is actually something I see so often in the professional tuning industry. A tuner will tend to approach every tuning job with a fixed air-fuel ratio in mind and simply apply that air-fuel ratio blindly to the car and send it out the door. Now, that's not necessarily to say that there's anything wrong with doing that, and yes, absolutely, we could have made the tune safe at 0.82 lambda. But by actually experimenting to see what the engine wants and what it's going to respond to, as we can see in this case, we could end up getting a significant improvement in power while maintaining reliability. If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.